Okay, I think let's start with this. uh, Previously, we finished this correlation matrix plots, and now we have to start from here, scatter matrix plots. And if we will move backward, then we are discussing multivariates plots, which is this category. So we are trying to understand data through visualization techniques. And for this multivariate plots, we have already finished this correlation matrix plots, and now we are moving toward the scatter matrix plots. So scatter matrix plots. So again, this scatter matrix plots will also show you that how the variables are related to each other, or how the variables are uh, have a relationship with each other, or you or in other words, how one variable is affecting the other. So basically, this technique is again for showing relationship between the variables. So we will draw something in two-dimensional, which means the x-axis and the y-axis. So horizontally or vertical axis, we will plot the data in these two directions. And now we are going to use the scatter matrix function, which is available in this plotly library, which is available for Python. So here if you will see these 5 lines, so we are importing plotly, which is a library, and in this library we have express. We are using that further module in it as a px, and then we are loading the px.data.iris data set. So this iris data set is available in this library, so I am not giving them the path. Okay, so I am not giving the path of the file because it is already by default available there. So we are directly uploading it from that plotly library px.data.iris. So iris dataset, which is a data set for the flowers. Okay, so that will be uploaded and this tf object will be created. Now here px dot scatter matrix, here we are using that scatter matrix function which I said, which is available in this plotly. So px is the handle for this plotly library, so that's why we are calling this px dot scatter matrix with the same handle, and we are passing this data into it, and we are setting the dimensions, which are the headers, which are the headings, column headings in the data set. So that one is sepal length, other is width, petal length, and petal width. So these are the headers, and then we are saying that okay, so we are basically uh, configuring this scatter matrix plot in this plotly library, and we are giving these arguments, and we are saying that we are going to use the color species, and there are other names also available for this color species and some others I don't remember. Okay, so maybe it is 4 to 5 or 6 other categories. Basically, these are the different categories to display these different styles. Okay, and one is species. one is species. So now this scatter matrix will be created, and this is the object for that fig, and then we are simply displaying fig dot show, and then it will be displayed something like that. And here, how what this picture is giving you an idea. So, for example, here, so here sepal length and the sepal length. So this column is the same, row and column is same. So that's why you are seeing that every data point is displayed individually in a linear line. So there is no relationship, linear relationship. And if you will move here on this, then these red data points which are drawn here on this on these green data points, so they have the same value, so they have a relationship. Okay, so they are in the same. So this is how you can identify. So the points which are mixing are overlapping on each other. So this is what they are affecting each other. Okay. They have a relationship. They are related to each other. So here sepal length and sepal width, and here this data is related to each other. So you can finally say that sepal length and sepal width are related to each other. And similarly here, okay, these data points, only minor portion. Rest, mainly the data is separated, but only minor portion. So you can say weak relationship, huh? And then here also you can say weak relationship because mostly data are separated. And here it has a not weak, okay, moderate, or you can say average relationship, huh? More than weak. So oh, this is how my pen is now disabled here. So this is how, so this picture, similarly, what else, where the overlapping is strong. So these two pictures have a strong overlapping, which means these two pictures have a strong relationship. Here the data has, so sepal length and sepal width, and similarly sepal width and sepal length has a strong relationship. And this has the minor, this has just a minor, here minor, here for example only this data, okay, more than minor, huh? You can say. So in this way you can conclude that the data in your data set have a relationship among different features or not, among different attributes or not. Now moving next to, so now we have seen the first topic, which is the understanding of data through stats, through numbers, and the understanding of data through visualization. So we are finished with that. So from these two things, you can identify that you have some issues with your data or not. But now the thing is, we have to prepare our data. We have to correct our data. Okay. So that's why now we are moving towards our that phase of preparation of data for the correction. Why this data preparation or the data pre-processing, same thing, okay? Why it is needed? Because we want to correct our data, and we want to input a correct data set to our model, and this will definitely, it will give us exact accuracy. I don't want to say more accuracy, exact accuracy, okay, real accuracy. So we want to feed the right data, and we want to feed the data in correct scale. Scale normally means it can be size, it can be dimensions, okay, number of features, or it can be the size of the data set. So, and we want that our data feed right data. What is right data means? The correct scale of the data, the format of the data, and it is containing only important features. Meaningful features mean important features. So these all three different things means contributes to the right data, and that right data we want to feed to our model so that the performance or the results that we will achieve would be real. There are different techniques available for data pre-processing. We will go into it one by one. Let's see with the first one, which is scaling. Scaling is, again, we will play with the it is sometimes it is called the size of the data, sometimes it's got dimensions, number of features, or the values in those features are. So scaling. So scaling is something we will balance, something. But what it is, let's see that. So normally in the data set, when your data points are a little far from each other, then you want to bring those data points close to each other, close to each other. This is called scaling. You want to bring the values of the data points or values of the features close to each other. So this is called the scaling. So this is called the scaling. Why we want to do that? We want to make a balance um, between the features. And when you will have that balance, it will improve the performance of the model. So this is a general sentence you can say after studying every technique. Here you are studying the first technique. When you will study second, third, fourth, what is the benefit? To improve the performance and accuracy of the model. This is the general statement. But what is scaling? Okay, scaling, when your values in the columns, in the features, are a little far from each other, or within the same column, when the values are far from each other, you want to bring them together. You want to bring them close to each other. So this is called scaling within the same feature or multiple features in the data set. How you can do that? So you will do what? You will do the values for the attributes, you will move them between 0 and 1. Between 0 and 1, like probabilities, but this is not that probability values. But you have to, whatever the values have, if the value is 5.4 something, you have to move between 0 and 1. If the value is 4.5 or 7 point something, or maybe minus something, you will have to move those values between 0 and 1. And when those values will be 0 and 1, you can understand that it would be automatically close to each other. Why we do that? Because there are some algorithms like gradient descent and uh, uh, k nearest neighbor. So these two algorithms normally use a scaled data, like this type of data. How we can do that? So we will use a min max scaler, which is available, which is a class available in the scikit-learn Python library. Let's see that. So again, we are using pandas and importing read. So that is the previous line that we are seeing from the beginning. So we are importing read.cv to read the CSV file. And then we are using numpy import set print options for the display only. So these lines which I have not highlighted, it is same like previous programs, okay? So I'm not, so don't expect that I will explain them, because from numpy import set print options, I will show you. Numpy. Yeah, this is set option from pandas, okay? This is different library. That is numpy. Numpy has a different syntax. But this is one set option that you have seen here. Here we are, this is same like numpy set options, okay? To deal with the display. Uh, I think we have used pandas only, huh? Okay. So here from NumPy, so now previously it was pandas, now NumPy and import set print options. So this is with the display like set precision 2.1.2. And then from sklearn and import pre-processing. So this is the new name for the scikit-learn, and here we are using pre-processing class from this, and this is the path of the Paima Indian diabetes dataset. Here here we are generating the headings for the columns in the Paima Indian diabetes set. There are 9 columns in it, huh? So here we are reading that file. So I'm not explaining too much. So reading and then creating an object for that file, data frame. Then values from that data frame, we are putting those values in this array, which is again an object to access all the values one by one. And then now here we are applying the actual thing, the scaling type thing. Here we are applying. So we are using this pre-processing class, pre-processing dot min max scalar, min max scalar. As we said here, use this one, and then feature range is equal to 0 and 1. Feature range, all the features would be between what? 0 and 1, the values. So the values would be what? What is scaling? Between 0 and 1. And here that is, we are giving that value. So it will set that min max scalar over this. And this is the object for that. And now, but this here, the min max scalar has not done the scaling yet. The data in the data set is not transformed yet, are not updated with the new values 0 and 1 yet, between the 0 and 1. So here we are doing that. Data underscore scalar, which is that thing, dot fit underscore transform. So this is the function that we are going to use, and we are passing this array into it. This is structural configuration. Okay, this line is a structural configuration, and here the data is available actually in this array, which we are passing into it. And now we are going to transform the data, whatever the values, 4.5 or higher or lesser, whatever, we are transforming. And here it would be transformed, and then you have a new object created, data, and the object is data rescaled. So now the data is rescaled, and this is the object to get that data, which we are getting in the next. Here we are set print options. Precision is equal to 1, which means we are displaying only one digit after the decimal point. And then print, okay, scale data, this is just a message. And then data rescaled, this is that previous variable, data rescaled. And rows from 0 to 10, okay, display from 0 to 10 rows, which you are seeing here, 0, 1, 2, 3. So these 10 rows. And here, value from the first column, value from the second column, third column, fourth, fifth, sixth, seventh, eighth, nine. There are 9 columns in Paima Indian diabetes data set. Okay. And this is the first row from that column. This is the second row, third row, fourth row. And if you look over here, now the values are between 0 and 1. Huh? Now the values are between 0 and 1. And if I will show you the data, this is also Paima Indian, huh? Because pregnancy, plus, press, and these are the different values, huh? Minus, positive, uh, hmm? Only for this data set. only for this data set, because all the values will be converted between 0 and 1. So then there is no point of negative anything, huh? Because the values would be between 0 and 1, which you are seeing here. Okay, now, second, normalization. So in this normalization, we will try to transform the values of each row to have a length of 1. For example, you have the rows. For example, here so this is one row. We want to transform the values of row so that if you will sum them up, it will have only length 1. It will have only length 1. So here we are not saying we are summing them up or whatever, because now the normalization have further two subcategories, L1 and L2. We will say these proper definitions there. So that's why here in the beginning we are just giving a general definition, that now we will try to rescale the values of each row so that it will have a length 1, so that it will have the final value 1. Okay, that would be called normalization. That would be called normalization. Why we use this normalization? This is now the question. If our data set is sparse, which means in our data set we have many values, uh, in our data set we have many zeros, values as 0, huh? Then that data set is called sparse data set. So if your data set is sparse, then this normalization technique is useful in sparse data set, because then after normalization you will have all your values, or all your values in the features, then they would be on the same scale after normalizing. Then those values would be normalized. Okay, don't use this word, because maybe this word is creating ambiguity with the previous term, huh? So then use another word. Okay, normalized, use a proper word, normalized, like you normalize the data in databases, huh? But this is different from that. Okay, here you have L1 and L2 normalization. Why we do that? The again the same sentence, to improve efficiency and performance of model. So now a normalizer class is available in this scikit-learn Python library. We will use that to normalize our data, and but there are two techniques that we have to study first. First is L1 normalization. So we will do what? We will modify the values in the data set, and then what will happen? For example, in a row, I'm not talking about columns. You have columns. For example, Pima Indian diabetes diet. For example, these are the column headings, and then you have values here. And then if you will apply L1 normalization, then the values in the first row, when you will sum them up, it will be equal to 1. Okay, it will be equal to what? 1. It will be equal to 1. That is called L1 normalization. That's why L and 1. L, and then from that 1 you can understand that you have to sum up each row, and it will be finally it will be 1. The other name for this L1 normalization is least absolute deviation. Let's see the code. So pandas same, numpy setup, print options same, sklearn pre-processing, and pre-processing. In the pre-processing, we have this normalizer available, which we are importing for normalization. Import normalizer. Okay, reading the database, generating the headings, reading the values of the data set and putting in this array. And then here we are configuring our normalizer. Normalizer, what norm, what technique of normalization we want to use? Norm is equal to L1. L1 normalization. We want L1 normalization. Dot fit array, and then we are passing this array into it. Passing these the values in this array, the values of all the data site row wise are existing there, and we are configuring this normalizer with kind, what is the kind? L1. So L1 normalization we are configuring here, and this is the object data normalizer created for this after this configuration. And now we are transforming. So data normalized dot transform. So mostly this function is available dot transform. And then we are passing this array into it again. Now the transformation would be applied on this array and the data would be normalized, which we have to display only. Which we have to display only. And in the next step, set printer, print options, precision 2. And then after that, this is the message normalized data and data normalized, which is that object. Huh? And here we are saying only three, displaying only 3 rows just to have a look on. Otherwise, we can display all. So 0 to 3. So here we are displaying 3 rows. And now if you will sum up these values, it will be equal to 1. A minor increase or minor decrease can happen, okay? 1.1 maybe, huh? Or 9.99999, okay? But it would be equal to 1. Similarly, if you will add up these values, it will be equal to 1. Because you are playing with the fractional numbers, so that's why it can be 9.999 or 1 point sometime 1 or something. So this is called L1 normalization. This is called L1 normalization. Number 2, L2 normalization. What is L2 normalization? So in L2 normalization, we will again modify the values of the data set. But how? In such a way that if you will take the square of each value, first you will take in a row, you will get the first value square, second value square, third value square, fourth value square, fifth value square, sixth value square, and then you will sum up all the resultant values. That would be what? 1. Sum of the squares of each value in each row. Huh? So the other name for this is called least squares. Let's see the code. So that is the same. Normalizer, loading the database, generating the headings, loading the values of that data set into this array, and then here setting normalized, and norm is what? L2, not L1. I think this is the only difference. Previously it was L1, but here we are doing L2. Fit array. And the rest of what? Rest data normalizer. Okay, data normalizer, transform, passing array into it. Here data is normalized, and here we are printing. And here you are seeing the output. And now if you will square it, if you will square it, square it, square it, square it, and after taking all the squares, and then when you will sum them up, the value would be almost equal to 1, okay? This is called L2. And from this 2, you can say it is a kind of a square, okay? From that L2, you can get an idea so that you will not forget the definition of L2. L2 means 2 means square. And L1 means, okay, you have to simply sum the values of the first row or each row, and then it would be 1. Now, Binarization.
In normalization, when you change the data to make the solution people want, for example, you are changing the original data. So you it's not the correct data because you change
No,
some part.
it depends on different model how your need is. Okay, so that's why, for example, that's why we said here. What was the example? Maybe here scaling or whatever. That in the gradient descent and the KNN, these two models required scale data. So this would not be the requirement for all the models. When you will study something about the models in the next CLOs, then you will understand which model has what type of requirement. But mostly this normalization is helpful because it removes also outliers. Outliers, you already, maybe we already discussed what is outlier. So yeah, if your data is scattered, so this is not a good thing. Okay, so then normalization which you will apply, that will be applied on all the points. So something like that. Okay, for example, if you have one picture like that, if I draw the picture like that, if you have some picture like that, which is not normalized, and now if I normalized, now this picture is smaller, and then data is something closer, huh? But the picture still has the same picture. For example, this here the dimension is maybe 100 by 100, and here the dimension is 10 by 10. Then you actually your values are still the same ratio, but it is now close to each other. Okay, it is now close to each other because you have applied that concept on all the values, not only that. So that's why we cannot say that it is not your real data. It is a picture of your real data. Okay, it is a picture of your real data. Okay, binarization from the word binary, 0 and 1. So it is again same but has a different technique. So binarization, in this binarization, you will convert your data into binary form, which means 0 and 1. You will convert all your values into 0 and 1, nothing more than that. But how you can do that? First, you will introduce some threshold. First, you will introduce some boundary. For example, zero point 0.5. And if and then you are saying that if your values are higher than zero point 0.5, you are considering all those values as one. And if your values are which are less than zero point 0.5 in the data set, you are considering them all zero. So zero point 0.5 and higher, all ones, and then lesser, you are considering them zero. And then you are converting all your values in the data set. And then finally, you will have 0 and 1 in your data set. So this is called binarization. How you can do that? We will have a binarizer class available in SK Learn. Let's see that. So here, importing read. Okay, this is the same. Importing read.csv. So in the processing, import binarizer class, and then okay, path of the data set, generating headings of the data set. Okay, reading values of the data set, and we will get these values through this object array. And then we are configuring our setting binarizer class with a threshold 0.5. And this is the threshold. Here you are giving threshold. This threshold can be 1, can be 5, whatever, it is up to you. So threshold 5 dot fit, and then you are fitting this array into it with this threshold. And this is the object for that. So it means that we can access now this binarizer with this object. And then binarizer dot transform, passing the array into it. Here the actual thing will happen. Here the actual transformation will happen. And your data will be converted into zeros and ones. And we can access that data through this object data underscore binarized, which we are printing here, data binarized 0 to 5. So first five lines we are displaying here. And here you are seeing these 5 lines with 1 and 0 only. And here 1 dot. You can use the set precision, and then precision is equal to 1, and then it would be 1.0, 0.0, something like that. Okay. You can do that stuff by yourself. But here we are not displaying anything, even a single digit after the decimal. So that's why it is 1, 1, 1, and here it is 0. Huh? So after binarization, you have your data now in this form. Let's move next. Standardization. This is a little bit detailed one, not like the previous one, which are a little bit simple. So here, what you have to do first, you have to calculate the mean, and then you have to calculate the standard deviation of the data. Okay, of the data that of the whole data set that you want to normalize. Okay, what you have to do? You have to calculate the mean and the standard deviation of the data. So here, for example, mean is the 0 and standard deviation is 1. And what is the next step? Then you will subtract this mean from the each entry, from the each entry of the data set. You will subtract the mean from one value. So there are many values there, huh? So from this value, you will subtract the mean from it, and whatever the result is, then you will divide that result by standard deviation. So 4 points in it. Number one, calculate the mean. Second is calculate the standard deviation, and from each cell take the value, subtract the mean from it. You will have some resultant value. Then you will divide it by the standard deviation. Then that value that you will get finally, that would be called a normal distributed value, or that would be called uh, Gaussian value. Okay, and in this way you will do this for all the cells. You will do this for all the cells, and then this value that you will get, that would be a normal value, normal distribution, Gaussian distribution, which means the bell curve, which means like you have seen something like that, huh? So the values which will lie in this curve are under this curve. So this is called normal curve. This is called normal curve or Gaussian distribution. Okay. It means that if our data set is not balanced, I'm using the word balance, general word. It means that if there are some issues with the data set, and if we apply this standardized, normally for all machine learning models, our data set should be in this form, in this form of Gaussian distribution. That is an ideal condition for your machine learning model. All the machine learning models mostly demand that your data should be in a normal distributed form. If your data set values have this form, then it is an ideal condition. And if not, then you can apply this standardization technique over it. And then your data set will be in a normalized state, in a standardized state, okay? Or in a normalized distribution state. So, and then when you have these normalized values or normalized data points, then you can use these data points for plotting similarities between them or are showing differences between them. Then you can use other techniques like Euclidean distance, cosine similarity for finding the similarity. When your data is normalized, now then you can do some other stuff. You can take this sentence as a simple that when your data is normalized, then you can find some other patterns from your data, and those patterns can be similarities between the data or the differences. And for example, here that these algorithm, linear regression, logistic regression, and many others, they normally assumes that our data should be in Gaussian distribution form. Our data should be in normal distribution form. Only then these models can perform better. Similar is the case with neural network. But normally sometimes people apply this standardization over the data set, sometimes not. So anyhow, we have seen what is the definition of standardization. Now we will apply the standard scalar class, which is available in the scikit-learn Python library. And here the mean is 0, SD is equal to 1. Okay, let's see that. From the pre-processing, import standard scalar. So still the same library is coming, sklearn pre-processing, and from that, this standard scalar is available. Minmax is also there available. Normalized is also available there. Huh? Here, binarizer is also available there. And in the pre-processing, normalizer is also available there. L1, L2, or whatever. And here we started from this pre-processing. Okay, the rest is minor difference. So I'm not totally using too much different libraries. I'm using one, and then if that function is available there in that library and it is more simple, then I'm using that source code. Okay. Otherwise, these functions, these L2, L1, these normalized functions would be available in other libraries also. But scikit is more famous for this mathematical and scientific calculations. Huh? Okay. Uh, here. So this is read CSV, and then okay, set print options, the previous one, data set, path, and generating headers, reading that file, reading the database, reading the values of the database, putting it in the array, and then here we are setting the standard scalar which we talked about here. Standard scalar dot fit, we are passing this array into it. Okay, now it is configured. We have the object data scalar for this, and then data scalar dot transform, and we are passing array into it again. Now this transform will do the actual thing, and the data would be standardized. You can use your own variable here. Data rescaled, you can replace it with data standardized. And then we are simply printing the message, and data rescaled, we are displaying 5 rows from that. And here you have the values. So these values that you have here is calculated after that concept of mean, standard deviation, subtracting mean from the cell value, and then dividing it with the standard deviation. So this is what now you have here. So this data that you have here is now normally distributed data. is now distributed according to the Gaussian method. Is now your data is under the normal curve. If you will draw, if you will plot it, then your data will draw a normal curve. Okay. And I will start next, inshallah, from here, data labeling and data encoding. Huh?